Yeah, so if you came to the first study session, you saw me try to do as much as I could of a bunch of problems, but I, of course, didn't get a chance to do everything because there's a lot to it. There's a lot of material, so in 2 hours, you can't hardly do 15 weeks worth of stuff. Um, but I'm going to recycle some of those same topics again tonight, but I'm going to use different problems. And I'm also going to try to hit a few of the topics tonight that I did not hit last night at all, so that this won't be just a repeat rerun for people who were already here last night. So anyway, some of these problems are coming out of the resources folder final exam problems, and others I'm kind of just winging it because I realized that there might be a problem that's not in any of those resources that would be helpful. And I'm going to start off tonight with exactly one such problem like that. So here is what I want to do, and this is something we didn't talk about last night, which is it's become through the years one of my favorite types of questions to ask. I didn't used to do this, but I want to give you a 4x4 matrix and ask you to do something with the inverse of it. So this is, let me just get the title here. So review session number 2. Right, and and I forgot to also mention, I did send out the solutions to that redo exam. So even if you didn't get your exam graded yet, it would not be a bad idea to read those solutions, or at least skim through them and see if that all makes sense. Okay, so let's get started here, guys, with the first problem I want to do. I'm going to give you a matrix A, and it's a 4x4 matrix. So I'm going to take this one out of the book, actually. So I kind of like the book's example here. So the first row is 0, -3, 2, and 2. Second row is 0, 1, 1, 1. And the third row is 1, 2, 3, and -4. And the fourth row is 1, 0, 0, and 5. And what I want to have us try and do is I would like to find the 3, 4 entry of a inverse if it exists. So we always have to add that little proviso if it exists, because if the matrix doesn't have not every matrix has an inverse, right? So we have to decide if this thing even has an inverse, and then if it does, we can try to find the inverse. So this would not be a very easy problem to do by the Gauss-Jordan method. But let me remind you, there's 2 different methods that we learned for finding the inverse of a matrix. 2 methods, right? In chapter 2, we learned the Gauss-Jordan method. That's the method where you take your matrix A and you augment it with the identity matrix, and you just do EROs. If possible, you try to get the left side all the way to the identity matrix. And if you're able to do that, then A inverse is staring right at you on the other side of that bar. So you immediately find the inverse that way. The trouble with this method, so this is the Gauss-Jordan method, the thing about this method that's really challenging is not making any mistakes on the EROs, because you have to do a lot of work to turn this matrix into the identity matrix on the left side. That's not just bringing it into row echelon form. That's actually going beyond that and doing a number of additional EROs to actually make it into the identity matrix. So there's a big amount of labor, I guess you could say, to try to get that right. And it's easy to make mistakes. So this is certainly a legitimate method, but there is a second method for finding the inverse of a matrix, and the second method is called the adjoint method. We learned this one just a week or 2 later, because this one has to do with the determinant. So I just remind you here, there's an actual formula for the inverse of a matrix is in terms of determinants. So the way this works, I'll just remind you again, is we have to take the reciprocal of the determinant of A and multiply it by the adjoint of A. Okay, so this takes us back. As you know, this is taking us all the way back towards chapters 2 and 3. The adjoint matrix, just again, a quick reminder about that. That is the matrix that you get when you transpose the cofactor matrix. So transpose is where you swap rows and columns. So all the rows turn into columns, all the columns turn into rows. But this is also kind of a lot of work because the matrix cofactors, every single entry, if it's a 4x4, there are 16 cofactors, right? So neither one of these methods is real easy to do by hand, especially if the matrix is getting bigger. The 4x4 is already getting up there as far as doing hand calculations. So the trick here, the way I figured out how to make a good question out of this is to not ask you to find the entire matrix A inverse. Instead, what I think is a good question to ask is to find one particular entry of A inverse. So like the 3-4 entry. So that would be the entry that is, 3-4 entries, that one right there. Yeah, row 3 and column 4. And I could ask you to specifically find that entry. Now, somehow that means we can make this an easier job, but not with the Gauss-Jordan method. If you're going to use the Gauss-Jordan method, I might as well just ask you to find the whole inverse because you have to do the EROs all the way across, the entire matrix. You can't just like focus your ERO into one spot because the different rows and columns affect each other, right? So, but if I ask you this kind of question, it is well suited to the adjoint method because we can pick off a specific cofactor that is in the position that we are asking for right here and do the calculation that way. So we did a couple of these, I think back in chapter 3, but let's try to do this example now. The 3-4 entry of A inverse. So for the solution, and guys, just stop me if you have any questions, okay? This is not like a lecture today. This is just me solving some problems, answering questions. We go nice and whatever pace you need, just let me know. Notice that for every entry of A inverse, we have to divide by the determinant. So I can go ahead right now and put that on the bottom. And then in the numerator, we have to figure out, in this case, I'll just write this into here. We need the 3-4 entry of the transpose of the matrix of cofactors. So that's going to be a cofactor because every entry of this matrix is a cofactor. But which cofactor is it? 4-3. Exactly. It is the 4-3 cofactor because, guys, when you transpose a matrix, you swap the IJ entries, right? So the IJ, if you transpose the matrix, it swaps the subscripts, right? That's what really happens when you switch the rows and columns of the matrix, the I's and J's switch. So you do need to remember that. You do need to remember that actually what you're being asked to find right here in the numerator is the 4-3 cofactor, okay? And both the numerator and the denominator involves finding determinants now. So we can work on either part of this. Let's just come down here to work out the determinant of A. That's probably what's going to take the most time. How would you recommend that I figure out the determinant of A for this 4x4 matrix? Cofactor expansion, awesome. And do you have a particular row or column in mind? What's that? Column 1? Yeah, I would pick a row or a column that has a lot of zeros in it. Your other option, and we haven't done it a lot, but another option is to do EROs on this matrix, and that requires you to remember the effects of the EROs on the determinant. So if I wanted to swap if I wanted to permute a couple of rows, that costs us a minus sign. If I want to multiply a row through by a constant, the determinant will multiply through by that constant. If I add a multiple of one row to another row, nothing happens. So if you're really not satisfied, let's say this matrix didn't have any zeros in it, right? You could, as a strategy, you could do some EROs that would bring some zeros into the matrix and help you. Okay, so in this case, we've got a couple of good choices, either the 4th row or the 1st column. Let's just use the 1st column since that's what you guys suggested here. I'm going to expand on column 1, and it's not a bad idea to show your work, tell me what you're doing so I can follow it easily. Now, when I go along column one, right, the first entry has a 0 multiplied with it, so I don't care about it. The second entry, don't forget about sign changes. Right, do we all remember this plus minus business? So in that first column of a 4x4, you see that we add the first term, subtract the second one, add the third one, subtract the fourth one. I'm actually gonna write minus 0, and then plus, and now we have a 1. So we write down a 1 here times the determinant of that particular minor. So I have to, maybe I'll do this with a lighter pen here. I have to cross off row 3 in column 1, and it leaves me with a 3x3 sub matrix. So this is going to be minus 3, 2, 2, 1, 1, 1, and 0, 0, 5. Okay, so we have that. I'll come back and finish that determinant in a minute, but I want to finish my calculation of this cofactor expansion first. So the last entry is going to be, turn this camera a little bit. We have a minus 1, and now I'm going to cross off. See, I have to try to bring a pencil or do it very lightly so you can kind of uncross these rows in case I ask you to do one of these. So now I cross off row 4 in column 1, and I have a different 3x3 submatrix, which is going to be, all right, this is the determinant of -3, 2, and 2, and then 1, 1, 1 again, and 2, 3, -4. Okay, so this is what we have to calculate to get the determinant of A. And for this first determinant, if you're sharp on your A game with determinants, you could probably tell me the answer just by glancing at it. See, because I can expand row 3 right here. 0 and 0, all I got left is the 5 times this little 2x2. And I can do this little 2x2 in my head. -3 minus 2, which is -5. So I have -5 being multiplied by that 5, that would be -25. So the first determinant is -25. Okay, and then minus, now this second one doesn't have any zeros in it, but it's only a 3x3. With a 3x3 determinant, we always can fall back onto the arrow method. Okay, by the way, I don't like the arrow method though, later in the semester. You remember when we have to find eigenvalues of a 3x3 matrix, the arrow method doesn't really lend itself to having a factored characteristic equation to come up with the eigenvalues. So as much as I love the arrow method, when we have a matrix of numbers, don't fall completely in love with it. Don't forget about cofactor expansion, because sometimes that's the best way to go. Now, anyway, so what we're going to have here, first diagonal is 12 plus 4, and then the next diagonal is 6. All of those numbers do not have a sign change. And now I go the opposite direction, and I have to do sign changes. So -4, minus -9, and minus -8. Okay? And guys, trust your instinct on this again with the grading of it. Okay, so I know I'm being a little harsher on grading the take-home exam, but I'm going to turn right back around again on the final. And because it's an in-class test, if somebody miscopies a number here or something like that happens and you end up with the wrong answer, you have to trust me. I'm not going to, totally mark you up with my red pen. Right? I might take off a point if I feel I need to. It would depend on exactly what the issue was, but this isn't worth spending a lot of time on because you can this is just easy math. I guess the 4's cancel. We have 18 plus 9 plus 8. That sounds like 35. Okay, so we have -25 minus, and then this becomes 35, I believe. 18 plus 9 plus 8. Yeah. So that's 35. So this comes out to -60. So that would be the determinant of this matrix. So far, so good. And that's going to go on the denominator right here. By the way, the other thing I want to mention, so I'll go ahead and put my -60 here. The 4-3 cofactor, remember that is intimately related to the minors of the matrix. It's actually just equivalent to the same minor except that sometimes, according to this picture, we have to do a sign change. And for the 4-3 position, which is right here, fourth row, third column, we do have a sign change. That little negative tells me to do a sign change. So I'm going to put that minus on that as well. So the two minuses obviously cancel, and we just have M43 all over 60. What is M43? Well, one more time, I go back to my original matrix. I cross off row 4 and column 3, and it leaves me with one last 3x3 determinant here. So what I'm going to have to do is the matrix 0, -3, and 2, and then 0 and 1 and 1, and then 1 and 2 and -4. And that's all over 60. All divided by 60 here, guys. And can we do that determinant in our head as well? One more time. Yeah, it's -5. If you expand column 1, right, you want to just beat your eyes in on those zeros, right? So in column 1, I only have a 1 times this little 2x2 submatrix, and the determinant of that is -3 minus 2, which is -5. Exactly. So that would be -5, and this is over 60. It is so easy to actually make sign errors on this stuff. There's no question about that. Because sometimes you get double negatives, sometimes even triple negatives coming in. Minus of minus of minus, that kind of thing. So just do the best that you can. But I think I did it okay. Any questions on that? Oh, yeah, you should have, yeah, okay. I'm gonna use the excuse, I was up till 3 in the morning. I'm pretty sure this should be -1 over 12. Oh my gosh. Send me back to college algebra. Okay, so anyway, that's the answer for this question. Okay. Let me ask a little follow-up question here. Are we good on that? Okay, so this is, I'm pretty sure we've seen these before. Follow-up question would be, find y in the solution to, and I'm going to make a system of equations now, -3y plus 2z plus 2w equals 1, and y plus z plus w equals 0, and x plus 2y plus 3z minus 4w equals 1, and x plus 5w equals 1. So this would be, I'm just making this up on the spur of the moment here. In this system that I've got on the board, I'm not asking you to solve for all of the unknowns. I'm just saying solve for y itself. Okay, so what does that remind you of? Yeah, this is where we can use Cramer's rule to solve for this in the same way that the adjoint method is favorable for picking off specific entries of A inverse. The Cramer's rule, which goes sort of part and parcel with the adjoint method, the Cramer's rule is basically a good technique for picking off specific unknowns of a system like this, right? So if I wanted to know what y is, then so for the solution, we might use Cramer's rule for this. I can't remember if I put one of these on your midterm or not. Did I? Okay, good. So at least we've seen this once before. But the way that this works, guys, is you just put the determinant of A on the bottom again. And on the top, you put what I called, and I don't know how standard this is, but the y is the second unknown. So I usually would denote that with what I call B2 here. And B2 is the matrix that you get by replacing column 2 of A with the right-hand side entries. Yeah, so in this case, oh, I have another question before I go on. How do I know that there will only be one value for y? It says find y. We've seen lots of, remember, any linear system can have either 0 solutions, 1 solution, or infinitely many solutions. If there's free variables, there would be infinitely many solutions. So we kind of have these trifecta of outcomes. How do I know that in this case, I am going to have a single value of y? Anthony? Because the does not equal 0? It does not equal 0, right? It equals -60, in fact, right? That means that the matrix that we are working with is invertible. By the way, does everybody see how this matrix is related to that problem? It's just the coefficients of the system here on the left, right? Guys, one way to do this problem is, of course, to write down an augmented matrix. You could write down A sharp and then do the EROs in order to solve for y. But again, the EROs could be quite tedious. Whereas we already figured out the determinant of A. As long as that's not 0, you'll catch yourself. If this matrix is not invertible, then you're going to get a 0 on the bottom here, and you're going to go, oh, well, that doesn't make any sense, right? So it has to be an invertible matrix. And in this case, because the determinant is -60, we're good to go on that. And then on top, we have the determinant of, I'm going to actually kind of write the matrix here if I could. I'm going to copy these right-hand side values into column 2. So the 1, 0, 1, 1, that's coming from right here. Okay, so this is how this is going to be working. Fabiola?
Why do we pick B2?
Because in my list of unknowns, y, which is the one they're asking us about, is the second one in the list. There's a B1 for x, there's a B2 for y, a B3 for z, and a B4 for w. In whatever case it is, you're taking this right-hand side list of numbers, and you are going to put them into the corresponding column of the matrix. You're going to replace them into that column. Yeah, good question. I'm going to move this over here a little closer. Sorry. Okay, so if everybody's all right with that, so that's the right-hand side vector. The rest of the matrix, we just refill it in the same. So 0 and 2 and 2. This is going to be a 0 and a 1 and a 1. 1 and 3 and -4. And then 1, 0 and 5. Okay, so this is what we're going to get. And again, now we have to do this determinant. Okay, so does anybody want to see me do another one of these 4x4 determinants? You know, we have a lot to cover. I think maybe, I mean, it's no different than the original determinant of A that we figured out. Let me just leave this to you to fill it in, okay? Because it's just, I would probably expand column 1 again, either that or row 2. Okay, be sure to look closely. You'd be surprised how many times I see people picking a bad choice of a row or a column. You really want to pick one that has lots of zeros in it, or at least as many as possible. Yeah, that's usually the best strategy. So anyway, I don't actually have the answer to that determinant, but maybe try it out, have a friend try it out, make sure you both get the same answer. That'd be pretty good confirmation. Okie dokie. Questions on that? Yeah.
In the case that this were on the exam and we just kind of forgot how the grammar rule worked, would you be able to just solve that using row echelon, or?
I mean, my guess is that the value for y right here, it already has a denominator. It's already a fraction with a denominator that's a double-digit value, which suggests to me that as I do these EROs, I'm not going to like what happens. And if I haven't found the entire matrix A inverse, it's going to be pretty tough. I mean, the thing is that what we're really looking at here, guys, is we're looking at a system that's of this form, right? AX equals B, and we're trying to solve for X. Because A is invertible, we actually could find X by doing this calculation here. X would be equal to A inverse times B. That is the unique solution for my unknowns. But the problem is, again, the hard part of this is it may take you like forever just to find A inverse. And I just hate to see you spend a huge amount of time on that. Yeah. So this one would be better to do by Cramer's rule. If if you just wrote Kramer's rule on your paper and nothing else, I would give you some points for recognizing that that's really what you should do. And if you wrote this down, I would give you even more points. So you see, as it just depends how much of this you can write down for me. The more you write down, the more partial credit you're going to get. And if you did everything except do this determinant, I could probably live with that pretty easily, because especially if you already did the determinant of A, that will convince me, okay, that person knows how to do these determinants using cofactor expansion, right? It's all about just trying to show me that you guys know how to do this stuff. So the engineering department doesn't come breathing down my neck that I didn't do my job right. So I have to do my best. Okay, so can I leave it at that? Okay, great. While we're kind of on the topic of playing around with these linear systems, let me do another example that's also off of an old, this is off of an old midterm. Let's consider, I'll state the question over here. Let's consider x plus z equals 2, and then ax plus y plus 4z equals 4, and then ay plus 4z equals b. Okay, and so the unknowns here are the x, y, and z. But what I'm gonna try to figure out here is I would like to find the values of A and B such that this system has, and now we're going to get into our trifecta of outcomes. 0 solutions, 1 solution, and the third case will be infinitely many solutions, infinitely many solutions. So those are always the 3 possibilities. Okay. Give myself a little bit of room here. It all comes down to where the pivots end up in the row echelon form of this matrix. That's the key to everything. I do have a video in the list that you'll find in the Canvas videos about the 3 outcomes of Gaussian elimination. And I really made that video to really emphasize that point. I really wanted to make sure that people were comfortable with that point. So the first thing we should probably do for this problem is what? Throw it into a matrix. Rubber stamp. I always know that's the first thing to do. So yep, I'm gonna start off, guys, by writing down the A-sharp matrix. So in this case, we're gonna have a 1, a 0, a 1, and I'm gonna put a bar here to augment the matrix, and we'll have a 2 on the right side. In the second row, I have an A, and then a 1, and then a 4, and then a 4. And then on the third row, I have a 0, and then an A, and then a 4, and then a B. It's gonna look something like that. Okay, and as best as we can, the idea here is going to be to try to bring it into row echelon form. I still, amazingly enough, after 15 weeks of harping on circling pivots, I have some people who don't do that very consistently, and it can sometimes cloud your analysis of what you are looking at. So I really encourage you to get those pivots circled. I already have one in the first row right here that I can use. Okay, now what I need to do is the goal with these EROs, right? And forgive me for sounding like I'm like going over some basic topic from like the 3rd week of the semester or something, but I do still see lots of people struggle with these kinds of things. So I'm going to do this problem just to practice it. In this case, I'm going to leave the first row alone because that's already good to go. We already have our pivot there, but the objective has to be to get zeros below that pivot. And in this case, I'm okay on the third row, but I need to get this A to turn into a 0. So to do that, I will actually label my ERO here. I'm gonna do A1, 2. And I just have to look at these two values, the 1 and the A. I need to take negative A times the top row and add it to the middle row. So A1, 2 of negative A. So we're gonna get a 0 here. And the 1 stays there. Now, if I put negative A times 1 and add it to 4, I'll get 4 minus A. And if I take negative A times 2 and add it to 4, I'll get 4 minus 2A. It's gonna look like that. Let's just recopy the third row as is. And I'm gonna circle my next pivot now. I'm good to go with a pivot in the second row like that. And I can keep going, I'm not done yet, so I need to get a 0 below this. The first column is great, but now I have a pivot in the second column and I need to have zeros below that. So I'll go ahead again, one more time. I'm gonna do this time A2, 3 of negative A. So the first row will not change at all. The second row will not change at all. Just gonna recopy those two rows, and now I have to take negative A times the second row and add it to the third row. Let's be careful with this. I have to take 4 minus A, multiply it by negative A, and add it to the bottom row. So negative A times 4 minus A actually gives me A squared, and then minus 4A, and then add that to the 4. Let's go look something like that. And I have to go one more time. I don't have a lot of room here. Let me just try to create some space right here. I have to take negative A times this guy and add it to B. So that's gonna give me 2A squared minus 4A, and then we add B to that. Okay. Now, I'm gonna be a little careful here about circling this as a pivot, because I actually don't know if A squared minus 4A plus 4 is a pivot or not. It could actually be equal to 0. And one thing for sure is you never want to circle 0 as a pivot. So I actually think that we are far enough along here that we don't need to do any more EROs with this, and we don't really need to worry about making any more changes with what we have so far. Let's start getting into the analysis now. So the first thing is that if this is a pivot, right here, I said if, because I don't know, but if this is a pivot, let me just lightly circle it. Then you'll see that I have no free variables. My unknowns, which are always aligned to those columns, my unknowns would all be pivoted. They would all be leading variables, which would mean that you could only uniquely solve for X, Y, and Z. There would be no free variables in that system. So if this was a pivot, then we definitely don't have infinitely many solutions. But we also don't have, you remember, what's the situation when we end up with no solutions? What has to happen pivot wise? In the far, far, far right column, yeah? So if my pivots go like this, guys, I'm safe away from that as well. I'm not gonna have a pivot in the far right column if the pivots go like they are shown right now. So let's just figure this out. When would this be a pivot?
That's not equal to 0.
As long as it does not equal to 0. It could be any other number, even if it was a 7. It's basically a pivot because you could multiply by 1/7 and create a 1 there. So as long as A squared minus 4A plus 4 is not equal to 0, this is going to give me one solution. And I don't know if you've noticed this yet, but this expression A squared minus 4A plus 4 is really nice. It's actually just the quantity squared of A minus 2. And so that just means that A should be not equal to 2. As long as A does not equal 2, we will get one solution. It's worth noting here that it doesn't even matter what B is so far. There is a B in the problem here, but as of right now, it makes no difference what it is. Okay, so for one solution, I've already kind of addressed the middle bullet point there in my three trifecta of possibilities. That would be if A does not equal 2. Well, the only other thing that could happen is that A could be equal to 2. So if A is equal to 2, I'm gonna go a little further with my analysis now. If A is equal to 2, then how does this matrix look? We could just write it out again. First row is the same. The second row, I'm gonna put in A equals 2, just so I can kind of look at it for a minute. Circle my pivots again. If A is equal to 2, I'm gonna get 0, 0, and 0. And then if A is equal to 2, this is my far right entry. What is this going to be? 8 minus 8 plus B, it's just B. There you go. Okay. So if A is equal to 2, then this is the matrix that we end up with, and how many solutions am I gonna get for that matrix, or do I know yet? No solutions? So in other words, this is a pivot? Does it have to be a pivot?
B doesn't equal to 0.
If B does not equal to 0. So let's just say if A is equal to 2 and B does not equal 0, then we're going to get 0 solutions. Exactly. So in that case, we would get 0 solutions. The only other scenario would be if A does equal 2 and B does equal 0. Guys, if B does equal 0, well then, then we have a whole row of zeros on the bottom here. And at this point, how many solutions would we end up with? Infinitely many, right? Because now the Z variable, which is the third unknown, has no pivot on it, which means that it is free, right? So it would be a free variable. So in this case, this would be infinitely many solutions. Okay. That looks okay to everybody? Yeah, so I've put questions like this on my exams before because it's a little bit of a chance to review the EROs, but mostly I just want people to understand these 3 outcomes of Gaussian elimination. Right? Every linear system has either no solutions or exactly one solution or infinitely many solutions. Of course, we've been solving systems all semester long pretty much ever since we got to chapter 2. In what case would the matrix be invertible? In terms of the, sorry, let me ask my question a little bit better. In terms of the little a and the little b, what would it take for this matrix, for the original matrix, which I guess is this one, which I guess doesn't have b in it. This matrix would be invertible. So let's just write it this way. A is invertible if and only if. What would be the requirement on the little a here? It would have to be the one solution outcome, which was this one, right? A is invertible if and only if A does not equal 2. Guys, that goes back to the invertible matrix theorem. That thing that's in the, back cover of the book is A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. We went pretty far through that list. Wouldn't hurt to take another gander at that. Just go through it and kind of get it fresh in your mind. Maybe not because of this, but I'm probably going to ask you something conceptual at some point on this test. And anything involving the invertible matrix theorem is really a good conceptual question. It really brings a lot of things together, right? Later in the semester, that invertible matrix theorem, it ended up getting related to things like linear independence and having a basis for Rn, stuff like that. And the row space of an invertible matrix is equal to Rn. The null space of an invertible matrix is equal to 0. So when we talked in chapter 4 about row space, null space, column space, when we talked about linear independence and spanning sets, all of that stuff had a bearing on this question of whether the matrix was invertible. Especially if it was a square n by n matrix in that case. So definitely something good to know. Any questions, guys, so far on anything we've been talking about? Okay. Well, maybe I should give you some other question. Let's move on to something else. Last night, we did a Bernoulli differential equation. Highly encourage you to make sure you know how to solve those. But I didn't do justice to the homogeneous differential equations of degree 0. So I would like to do one of those tonight. And then let me find the one I want to do here. So let's solve. So this is what number am I on? 3? 3? Okay, number 3. Thank you. Number 3 is going to be the following problem. I'm going to try to solve, I'm just pulling this one out of the book here. 3y squared plus x squared minus 2xy prime equals 0. Okay, so I don't think we've looked at this one before, and I think it might be good to do so. If you were here last night, you may remember I talked quite a bit about the 4 types of differential equations that we have from chapter 1. Separable, linear, Bernoulli, and homogeneous. And one of the things I mentioned last night was that when you have lots of pluses and minuses in the equation, it's very hard to separate it. It's unlikely to be separable because you can't very easily like split apart. Like I could like move this term to the other side, but I can't really split this plus sign apart. These 2 terms are like married to each other, right? So somehow you can't, if you could factor it, maybe, but you can't really factor, like this term has only y in it, this term has only x in it. They have nothing in common. I don't see any factoring going on with that. So it's kind of hard. But separable differential equations can be tricky because even though the method is very natural, you just separate the equation and then integrate both sides. But it can be tricky because the algebra that underlies that, right? Doesn't look separated now, but maybe we could separate it, right? That's always the thought in my head. But if I'm going to do that, it's going to be an algebraic manipulation. Okay, and I could spend 500 hours talking about doing algebra. And it may not really help all that much. So that's just something you guys have to be able to do. You have to be able to carefully manipulate equations like this. What's maybe a little bit easier is to, maybe you could figure out that it's separable by process of elimination, right? Because we know that a linear differential equation has to look like this. Okay, so I wrote this down last night, but I just want to get it up here again for anybody who wasn't here last night. And even if you were, it never hurts to see these things more than once. Guys, linear differential equations, linear differential equations, that's cute, are very, very common. First order linear differential equation. And remember that these are solved by using integrating factors. Okay, so you have to remember a few things. The integrating factor is this equation right here, okay? E to the integral of p of x dx. But see, this is something that it's a very black and white issue. Is your equation in this form or not? Can you put it in this form or not? It's usually pretty easy to see that. There has to be a y prime, there has to be a y, and everything else is x's. Okay, so the linear equations, I personally think, are easier to identify. And then the Bernoulli one is not that much different than that. The Bernoulli one, and again, we did Bernoulli equations last night, so I'm not going to talk a long time on this right here, right now, but you definitely should review this. The only difference between a linear and a Bernoulli equation is that the right-hand side of a Bernoulli equation will have y to a power on it. This is y to the n here. And for this one, you have to do a change of variables, and it doesn't hurt to write that down again tonight too. The change of variables that we pulled out of the sky way back in the dark days of January is this one right here, u equals y to the 1 minus n. And that will turn your differential equation into a linear one. The linear equation that you get, I guess I'll write that one down again one more time too. So I've written this down both nights now. Hint, hint.
It's a big problem.
So. So there's the new linear differential equation that comes out of, can I be any more subtle? There's the new linear differential equation that comes out of applying this change of variables. Okay? So remember that the n is just a constant number. So what's happened though is that in the equation here on the bottom, I don't see a power of u on the right side. Whereas I started with a power of y on the right side. You can just memorize this. I do have I think I mentioned back when we were learning this, that there's a 3-minute video that I made where I derived it, that if you apply this change of variables to this equation, it'll turn it into this. But nobody, well, I've seen students do it before actually, where they actually derive it on the exam, how to get this one from this one. But you don't really need to make your life harder than it needs to be. I would probably just make sure you know this one here, okay? So that would be very, very helpful. Again, Bernoulli equations are easy to recognize. They look almost like linear equations. The only difference is there's somewhere along the line you have a power of y. That power could be a negative power. It could be a fraction power. It doesn't have to be a big positive whole number. It could be any value of n, positive or negative or fraction. But these are usually easy to figure out. And yeah,
I know we probably won't see one in an exam, but can it be irrational?
irrational, n could be irrational.
Yeah.
Well, that's an idea. You're gonna get in trouble now. Don't give me any ideas. No. So yeah, it's usually gonna be a relatively nice number. Yeah. So I will tell you the honest truth. When I see a differential equation, the first thing I do usually is I try to figure out, would it be one of these two? And you know what? I can tell immediately that it's not, because if I have y times y prime, they're right hitched together in a product. Well, I don't see that here or here, right? Y times y prime does not occur. So this is not linear and this is not Bernoulli, right? So the only other choices are if it would possibly be separable. That's always a murky one for me because I'm like, I don't know, maybe I'm just not thinking of the right algebra to do to get it separated. The other option though that we can also play with is homogeneous. Let me remind you about the homogeneous differential equations. To explore that, what you need to actually do is solve for y prime. So if I was to do that, so I write this as 3y squared plus x squared over 2xy. And the way the homogeneous equations work, I did mention this last night, but I didn't really do an example of it. So the way this works is that everywhere you see an x, you change it to xt. And everywhere you see a y, you change it to yt. So let's just do that. Everywhere in this expression that I have an x, I'm going to change it to xt. By the way, be sure to use parentheses around these things. If you don't put parentheses around the yt, you're going to get confused with it a little bit. But everywhere you see a y, you change it to yt. Everywhere you see an x, you change it to an xt. And the question is that still the same? So you can ask yourself about that. I see that there are a t squared here and here. If I factored that t squared out, look what I have on the bottom to cancel with it. T squared, right? So actually it is going to completely cancel out. And so that really gives me, and it basically tells me that this is homogeneous of degree 0. Okay, so let's just write that down. This is homogeneous of degree 0. And how do we solve such an equation? There's another change of variables, and I did not go over this last night, so I definitely want to mention it now because I also really like these equations. The homogeneous equations of degree 0, they always turn into separable ones, right? So if we do this change of variables here, guys, everywhere we see a y, we change it to xv. And in the process of that, the derivative of y can be written down using the product rule. So x times v prime plus v times x prime, well, x prime is just 1, so we just get v for the second term there. And what I'm going to do is I'm gonna take this equation, notice I solved it for y prime. It was not given to me that way, so I did have to rearrange it a little bit, but I solved it for y prime so that I can now just directly replace the left side, and I'm gonna do this, I'm actually gonna implement the change of variables here. The left side, which has y prime, is gonna turn into xv prime plus v, yeah? On the right-hand side, everywhere I see a y, I'm gonna change it to xv. So this will be 3 times the quantity xv squared plus x squared, and then on the bottom, 2x times the quantity xv. Okay, give myself a little more room now. Now, this should be separable. I'm not saying it'll be easy to separate it, but it should be separable. Actually, if you take a look here, guys, you see that on the bottom of this fraction here, on this right side, on the bottom of this fraction, I have 2 x's. On the top of the fraction, I have an x squared here and an x squared here. If I factor that x squared, maybe I could skip a step and just cancel it with the x squared on the bottom. So what I'm left with, if I do that, I'm gonna leave the 2v on the bottom. And then on the top, I've got the 3, but I've already canceled the x part, so it would just be 3v squared, and then I would have a plus 1 on the end of that. Okay, so this gives me x v prime plus v, that's on the left, and then on the right, what I have is this fraction here. I would probably break this up into 2 pieces. So it would be 3/2 v plus 1 over 2v. Yeah, so it's gonna look like that. Hold this over here again, a little bit closer. Okay, we have to do a little bit of work on this, right? Try to get it cleaned up, so I can see that there's a v on the left side and there's 3/2 of a v on the right side. Let's just cancel that a little bit. So this is just going to be x v prime equals, what is it? V over 2 plus 1 over 2v. And in anticipation that this is going to be separable, it always helps with separable equations to not use the prime notation for the derivative. It's better to use the notation of dv over dx, like so. And on the right side now, I would probably turn this into one single fraction that has a 2v for the denominator. If I do that, I have to get the numerator right. There's a 1 there. So 1 over 2v, but then what about this one? It's v squared, exactly. It's gonna turn into v squared plus 1 like that. Okay, so now I'm gonna do something and see what you guys think. I'm going to try to get it separated. So what do you guys think about this? That be okay? In 3 semesters of taking calculus, did you ever see your professor write dx in the denominator or the dv in the denominator of fraction? I hope not. If so, I want to know their names. Anyway, no, that's not going to work. It's just not, you can't integrate that. But I've seen people do this and then they integrate it. So, oh, the integral of x is x squared over 2. Actually, this was supposed to be a 1 over x. So they're getting completely the wrong answer now. So you have to flip this the correct way. Let's erase that and try one more time. I'm going to take the dx over x and flip it to the other side so that I can put the dx on top and put the x on the bottom. And then on the left side, I have my dv here, and let's just check it out. The 2v needs to be moved over, and then I have a v squared plus 1 like that. Okay. All right, so that is now separated, and we should be not surprised by that because it was supposed to become separable. the homogeneous of degree zero equations, they always become separable, actually. Okay, and so once they are separated, then what you have left to work on are the integrations, okay? And I try to be gentle with you guys on integrals for the most part if I can, but you should be able to do some of these basic integrals. The right-hand side is very familiar. What's the antiderivative of 1 over x? Natural log, very good, of the absolute value of x. I should stick a plus c on the end of that, because it's a general antiderivative. On the left side, how would I integrate 2v divided by v squared plus 1?
So,
Exactly, it's a u substitution where you let u equal the v squared plus 1, right? So there's a u on the bottom and then the du. Okay, so just, I'll make a very small note here. U is equal to v squared plus 1, so that du is 2v dv. So the whole thing on the left side becomes du over u. And when you take the derivative, when you take the integral of that, again, you get a natural log of u, but I'm gonna go right ahead and put that back in terms of v. So the natural log of u is just v squared, is the natural log of v squared plus 1. Yeah. Okay, so am I done? Edgar?
The C you write from the part that has the X on it, right?
Actually, you can put the plus c on either side. There's a plus c on both sides. But actually, the plus c on the left side and the plus c on the right side don't have to be the same plus c, so they wouldn't necessarily cancel out. And you'd have more constant on one side than the other, and if you just kind of subtracted or combined, you'd end up with plus c on only one side. So it's sufficient to just put it on one side. I will usually put it on the side that is away from the unknown function that I am looking for. Because after all, you're trying to get the unknown function by itself. And the more stuff you put over here on the left side of the equation, the longer you're gonna have to work at it to isolate the function. So I prefer to put it on the side with x. I think I've probably done it that way every time. So I kind of hinted at this, we're not really done yet. If you stopped right now, you'd get a good chunk of credit because you recognize it's homogeneous, you tested that, you did the right change of variables, you did the algebra to separate it, you even did the integrals of both sides. This is pretty far along. But we're not quite done yet because we need to solve for, well, ultimately we need to solve for y. And we don't even have y in the equation yet. So I would like to solve for v at least. And then once I know what v is, we have an equation on the board there that'll allow us to get y again. So to solve for v here, what would I need to do? Exponentiate it, you got it. Because of these natural logarithms, I want to get rid of those by exponentiating. And whenever you exponentiate a log, the two operations cancel. So you would leave yourself with v squared plus 1 on the left. And now here is one of the algebra hangups that people have is simplifying these exponentials. This is e to the, whatever you want to call this, a plus b. One thing plus another thing. That is the same as e to the first part times e to the second part. Make sure you get this right. I may never see you make this mistake, but don't let your engineering professors see that, right? There's no plus here. This is now totally a multiplication. What I can do with this is replace the exponential of the log with just the absolute value of x. And then e to the c, technically, it should be changed to c1 because it's not the same number. If c was equal to 3, then e cubed is not the same constant. So I would prefer to change it to a c1. If I'm not going to do that, I might as well just leave it as e to the c, which would be okay. Okay, but I usually don't take off points if people accidentally just call this c again, but it's technically not the best thing to do. So we'll just call it c1 for right now. And then I'm still trying to isolate v. So if I want to get v, I need to take the c1 absolute x, subtract 1, and then take a square root. So I'm doing a couple of things at once here. But this should be getting us pretty close. The last thing I have to do once I've figured out what v is, I know that I can solve for y by just multiplying v by x. So if you have that change of variables written down, it's easy to just look that up. So y is equal to xv, which would in this case just be x times the square root of c1 absolute x minus 1. Okie dokie. So between tonight's example of a homogeneous differential equation and last night's example of a Bernoulli equation, we've actually practiced all four types of chapter 1 equations, because Bernoulli equations required us to solve linear ones, and homogeneous equations required us ultimately to solve a separable differential equation. Okay? If you need a little more practice on this, of course, one thing to do would be to go back to your first midterm and or the sample midterms for the first midterm. The other thing you could do is look at, I think it's group works 2 and 3. Way back in the beginning of the semester, we did a few group works where I gave you some differential equations and I just asked you, what type of equation is this? And asked you to work on that. So are there any questions on any of that? So far, so good. Hopefully, all right. Let me see. Oh, I don't want to do that one. Yeah, let me back over here and give you guys a couple of theoretical questions. It's not erasing very easily tonight. Okay, where is that other problem I wanted to do though? Yeah, here we go. Okay, yeah, so let's just try this question. This is number 4. Yeah, number 4 here. Okay, so let's try to talk about this problem really quick. Let's assume that x prime is equal to the matrix 2, -1, and 2, and 4 times x. And I would like to ask you, as t goes to infinity, t is the independent variable of this linear system of differential equations. What happens to the solution curves? Remember how we were talking about this idea that you at time 0, you're dropping your feather into this picture and allowing time to roll forward, you sort of track what happens to that feather based on the currents on the surface of the ocean, if you want to think of it in that kind of a context. So what do I need to do for this problem? Find the eigenvalues, right? Okay, so let's do that really quickly. Okay, so this is maybe a little more recent material, but that's okay. Let's just see if we can get the eigenvalues. This is a 2 by 2. So I have 2 minus lambda and then -1. Then I have 2 and then I have 4 minus lambda. Okay, so subtract lambda off of the main diagonal and that's what we would have. So this becomes 2 minus lambda times 4 minus lambda and then plus 2. I'm going to multiply this one all the way out because it is only a quadratic and I don't mind quadratic equations. So I'll have lambda squared minus 2 lambda and minus 4 lambda makes minus 6 lambda. And then I have 8 plus 2, which is actually 10. So check me on the math if I get anything wrong. We're going to set this equal to 0 as the whole idea. So I'm going to look for the eigenvalues now of this matrix. So what do I need to do to get the lambda values here? Yeah, this doesn't factor nicely. It does not have an easy factorization. So I would use the quadratic formula for this. So I would take the negative of -6, which is 6. And I would do plus or minus the square root of 36 minus 40, all divided by 2. And this is going to be 6 divided by 2, which is 3. And then plus or minus Yeah, 2i over 2, which would be an I, exactly. So 3 plus or minus 2i, those are the eigenvalues. So hopefully you guys remember how this is gonna work out, is you're gonna get solutions that are gonna have, e to the 3t. Right, the real part of the complex root goes here as an exponential. And then you end up multiplying by cosine of t plus I times sine of t. And then there's an eigenvector here. Which I think you guys mostly are, especially on the little redo midterm, people were doing a great job on this. So you get something that you can then floy out. So you just have to floy this thing out eventually. But the main thing though is what is going to happen to the solutions as t goes to infinity in this case?
So source.
It's unstable.
I don't think it's a source. I'm sorry?
Spiraling outward.
Spirals that go outward. So sources would be, a
Oh,
source would be if there were two real lambdas that were both positive. Here we have imaginary numbers, so the solution curves here, guys, are going to, as we kind of talked about this, they're going to make spirals. So you're gonna get an outward oriented, you have to draw arrows on those pictures. I'm not gonna worry about whether it's clockwise or counterclockwise, or exactly what the slopes are at any given point. That's a little too technical for a hand drawing of these things. But the general idea of the solution curves is gonna be like that. And so the idea is the answer here would be all solutions spiral outward towards infinity.
Do you want us to draw a diagram of the test or?
Wouldn't hurt. Yeah, it wouldn't hurt. Yeah, I mean, it's if I really want to see it, I'll probably ask you directly for it. But yeah, it doesn't hurt to draw that. Actually, I have to tell you, I am lying to you a little bit with that answer. There is one little sort of asterisk about it, that there is one little thing that I should qualify that answer with. Does anybody know what I'm talking about? I have not ever actually mentioned this before.
That one of them is gonna be equal to 0.
If I dropped the feather right at the origin, okay, like the eye of the hurricane, right, is totally calm there. The currents are spiraling around the origin, but right at the origin, if I happen to have an initial condition that was x of 0 equals 0, 0, then this would not actually be correct. All solutions except one spiral towards infinity. So I'll just say except the solution with x of 0 equal to 0 and 0. Why is that? Well, it's just because when you write out the general solution down here, this initial condition, well, so you know how this all works, right, guys? You have, C1 times something plus C2 times something. If you plug in 0, 0 as your initial condition to this thing here, then what you're actually going to get is that the constants are both 0. So I don't care how big of an exponential, factor you have in your terms. You might have a big e to the 3t sitting in here that's blowing up. But if it's being multiplied by 0, it doesn't matter, right? It ends up becoming 0. So it's just something to kind of keep in mind that you have to be aware of. But yeah, for the most part, all of the solutions would spiral outward to infinity, except for that one. That's exactly right. Okay, let's do another problem. I'm gonna do kind of a little short mini series of what I would call theoretical problems. I don't know, that one isn't all that theoretical. It's mostly computational as well. Okay, let's try this one. So I'll call this number 5, I guess. Assume And by the way, I'm jumping around with the topics and I'm kind of doing that on purpose because I think that's the way people do exams. They kind of jump around and solve whatever they can, whenever they can. So I'll do that too. Let's assume that A, which is n by n, and B, which is n by n, satisfy S inverse times A times S equals B. That might remind you of the equation that we come up with normally when we do diagonalization. Normally with the diagonalizable matrix, you would have S inverse times A times S equals D. And the D is usually the diagonal matrix with the eigenvalues of A on it. But I'm not assuming that here. I'm taking out the D and I'm just saying, suppose there's another matrix B right there. When you take Math 307, what they're gonna tell you is that, oh, that means that the matrices A and B are quote unquote similar matrices. So two matrices are similar if I can go from one to the other by what we call conjugating the matrix A by S with S inverse. So this is a basic assumption that I'm gonna make right here. Of course, we didn't learn about any of that stuff, but I can just give you this equation, right, to start with. Okay. And then let's suppose that V is an eigenvector of A corresponding to lambda. So maybe we have that correspondence. And then I would like to prove, so this is actually a proof. I would like to prove that if you take S inverse times B, okay, that this is an eigenvector of B. I'd like to show that that's an eigenvector of B, and I'm not telling you what the eigenvalue that goes with it is, but we'll have to figure that out as part of working this problem out. Okay, so kind of an interesting one. I've asked questions like this before, but usually it's been with something like, you know, eigenvectors of A become eigenvectors of A squared and A cubed, and you can make equations just with A. Here I've kind of introduced two things at once. So, but this is a perfectly good question. I've used it before many times. It's a good tester on whether you really can manipulate the eigenvalue eigenvector theory from an abstract perspective. Okay, so because we get very hung up on doing the computational side of it, and that's great. I want you to be able to do that too, but I do also want people to still remember the background, the basics of it. If you didn't have any idea what to do right now, how to do this problem, what would be at least something that you would probably write down? Yeah, I would definitely do that. B is an eigenvector of A corresponding to lambda. So I want to make sure Dr. Annan knows before he tries to go away for a nice summer, that all of his students know the most important equation in the eigenvalue eigenvector theory. So we have A times V is equal to lambda times V. If we don't know anything else, we should at least write that down, because I'm gonna for sure be happy to see that. Okay, and now I want to prove that S inverse times V is an eigenvector B. By the way, just so you're kind of understanding this, S inverse will be an n by n matrix. And the vector V, as you guys know, when you find eigenvectors, we usually draw them as columns here. So I have some column here, this would be V. So S inverse times V, if you actually did this matrix multiplication, you would get another, you know, vector that's kind of in the same column format. Right? So that is, so when I write S inverse times V, that actually does make sense. Like I can actually multiply those things together and have it make sense. Does anybody have an idea how I might approach this?
Yes, there's B S inverse B is equal to lambda S inverse B?
Okay, very, very close, very, very close. You know, so if V is an eigenvector of A, that tells me I'm gonna look at AB. So if I'm trying to prove that S inverse V is an eigenvector of B, what I should do is I should take B and I should try to apply it to the vector that is under consideration, which in this problem now is S inverse times V. So I would like to say something about this. Right, this is what I'm gonna look at, B times S inverse V. And as you guys know, we don't really need parentheses on these things because everything is associative with matrix algebra. So I'm just gonna write that as B times S inverse times V. Now, can I do anything with that whatsoever? At some point, I want to use the blue part. But I can't really use the blue part if I don't see an A in the matrix in this equation anywhere. Right here, I don't have an A anywhere in front of me at this moment. And I would need to have that in order to even dream about using the blue thing, but the blue thing has got to be important. Go ahead, Edgar.
What if you like start playing with the order of S? That given thing, yeah.
Yeah, this thing here, somehow, if I see B times S inverse here, I'm kind of thinking about it in terms of where it could show up here. So I've got B on the right side, but I would like to have like an S inverse next to the B. So can I get that? I can take this equation, right, and I can multiply it by S inverse on the right of both sides. Right, so what I'm saying is that, let me just put a little asterisk here. And I'm just gonna right multiply, guys, by S inverse. Okay. And when I have an S next to an S inverse, of course I can cancel it. Right? So now B times S inverse can actually be changed into S inverse times A. That is how you're gonna get the A into the game. So coming back down here, B times S inverse is the same as S inverse times A, and then that's times V. Okay. So I literally just left the B in the same spot, and I just took the B times S inverse and changed it to S inverse times A. Are we seeing that? Just from rearranging this thing. Now, okay, I see the AV. Bells start going off in my head. AV is the same as lambda V, right? So let's just see if we could plug that in. So the S inverse stays there. We have lambda V going in for AV. And what do you want me to do with this? Because we're almost done.
Call it lambda.
Lambda is just a number, right? So that can float anywhere, beginning, middle, or end, doesn't matter. Let's put it out in front. And after we put it in front, I'll group together the S inverse with the V. And what you guys, I hope, are recognizing now, what I hope is maybe starting to materialize is, look where we started. B times the vector equals lambda times the same vector. If you call this vector W, for example, then what you really have is B times W equals lambda times W. It sounds like our famous equation relating eigenvalues and eigenvectors. So that actually does it. And notice that the eigenvalue here is the same lambda. It didn't change at all. It's the exact same lambda from what we had had before. Okay, does this make a little sense? Pretty good likelihood I'm gonna have this theoretical eigenvalue, eigenvector stuff somewhere for you guys to show me.
Is the trick to these to always like look where you can multiply something to the right or to the left?
You know, I don't even go into that much detail with it. I just look at this and I say, how am I gonna do anything with this? Like, what have I been told that allows me to work with this? The problem is abstract enough that I know it has to come from the given information. It can't be some like computational thing. It has to be something from up here, and I can just. I think for me, the trick is really that I need to get the B back in terms of the A somehow. Because I know from the beginning that I can change AB into lambda B. But I don't have A here. So for me, the trick is how can I get the B out of there and get the A in there? And this is the only equation that gives me any hope of doing that. This is the equation that allows me to sort of transfer from B to A and back and forth again. Yeah. By the way, can I cancel the S inverse and the S right here? No. Please don't. There's still a lot of people doing that kind of thing. Unless the matrix and its inverse are directly next to each other, they cannot be canceled. The order of matrix multiplication makes a difference, right? We are not allowed to just float matrices past each other left and right. So you cannot cancel. I mean, gosh, if you were able to cancel the S with the S inverse, then you would be saying that A equals B. So then suddenly the problem isn't very interesting. There's only one matrix there. So yeah, so be careful about, don't invent any rules of linear algebra that are not allowed. Yeah. Okay, questions on that? Seem okay to everybody? Yeah, okay. Oh, here's my sheet. Okay, let's do another one. Oops. That's number 5. Oh, I told everybody last night, so I might as well tell you guys all again tonight. I decided I'm not gonna do any mixing problems. Random comment. Chapter 1, we did mixing problems way back as an example of differential equations in the first week of the class. I've just decided there's enough other stuff. I don't need to give you that because there's a whole. I mean, it's not that hard, but those are word problems that you have to plug a bunch of numbers into, and I'm just not. I'm not feeling like it doing that. Okay, let's take a look at this. Yeah, number 6. You guys okay?
Yeah.
You sure?
Sorry, can you just
Yeah.
re-explain like how we get from there to like the S -1 EB?
To this one.
Yeah,
Oh, okay, yeah, so let me just start off with the original equation. This is what we started with. Okay, so what I did is I just took this equation and I put an S inverse on the right of both sides. So whatever I do to the left side, I have to do the same thing to the right side. So that's basically what I did. And then whenever so I cannot cancel this S inverse with the S,
Right.
but here they are right next to each other, so I can cancel them. And when I cancel them, what I really mean is it turns into I, the identity matrix, which is like multiplying by the number 1. So it sort of just disappears. And so then what happens is all that's left on the left is S inverse times A, and all that's left on the right is B times S inverse. So all I did actually is I took this B times S inverse and changed it into S inverse times A right in this step. The V just comes along for the ride. It doesn't get affected, it doesn't change, it's just being recopied down. And I'm literally just going from there to there.
Okay.
Is that okay?
thank you.
Yeah, good question. That's fine. Okay, so let's try again. I'm gonna jump a little bit more around here, guys. Let's assume that A is 4 by 4 and B is 4 by 4 with the determinant of A equal to -2 and the determinant of B equal to 3. Okay, so what I wanna do, guys, is I would like to find the determinant of the transpose of the quantity of A inverse times B times the matrix two B quantity inverse. Another sort of more abstract problem. So I don't have a specific matrix A or B. I do know the size and I know what the individual determinants are. But then I'm giving you this, a more complicated thing, and I'm asking you to figure out the determinant of this. And what I'm really getting at here is the properties of determinants. How do they behave with inverses, with transposes, with scalar multiples, with multiplication, all that kind of stuff, okay? Notice the one thing you don't see up here is anything to do with addition or subtraction. That's because, as we know, there are no nice properties for determinants when you add or subtract matrices. So I can't really expect anybody to do something with that, but this is pretty doable. Does everybody think they might know how to break this down? It's not a hard problem, but it's been 10 weeks since we played with something kind of like this. Remember that determinants completely respect multiplication. So I can figure out the determinant of the first part separately from the determinant of the second part, and then just multiply the results. So what you would do here is just break this thing down, right? So this would be equal to, you know, the determinant of the first one, which is A inverse B transpose. And that would get multiplied by the determinant of the second one, which is the inverse of two B. It is important to keep parentheses around. If you don't put the parentheses around the two B, you might think that this is 2 times the matrix B inverse, which would give you the wrong answer, actually, at the end of the day. Okay, guys, remind me again, what effect does the transpose have on the determinant of a matrix? A transpose? Actually, there's no effect at all. Yeah, this one has no effect at all. The minus sign comes in if you permute 2 rows. Yeah, exactly. Permuting 2 rows is not the same thing as taking a transpose. So this transpose does nothing at all. And then inside of here, maybe I'll just write it out one more step. It's always good to show the work step by step. So I can split up the A inverse and the B also because it's a multiplication. And then I guess I'll just leave this the last one here for a minute as well. The determinant of the inverse of 2B. So now I've got 3 things multiplied together. Okay, can somebody remind me? I'll come up here to continue. Can somebody remind me how the determinant of A inverse is calculated? It's 1 over, exactly, 1 over the determinant of A. So I'll just write that for a moment here, 1 over the determinant of A. In a minute, I'll start plugging the numbers in. So then we get times the determinant of B. And then we're also going to get, and there's another inverse here at the end, 1 over the determinant of 2B. Right, so it's gonna be something like that. And we're just about in good shape now. The determinant of A was given as -2, right? The determinant of B was given as 3. And what about the determinant of 2B? Do you guys remember what that does to the determinant? Yeah, the tempting thing is to just pull the 2 out. But remember that you're really multiplying every row of B by 2. And B has 4 rows. That's why I gave you this information. Each one of those rows is like scalar multiplying a row by 2. So that happens 4 times, guys. So it's 4 times that we have factors of 2 that get pulled out in front. And then the determinant of B is all that's left. And that gives you a 3 there. So this is it. The 3's actually cancel. And we have a minus 1 over 2 to the 5th, which is 32. So it would be -1 over 32, if I did that right. Okay, so in one problem, I can test like all of the determinant properties, which is kind of nice. Okay, one more theoretical one. And hopefully you guys are not hating these. See, I like the theoretical ones. I do one of these 5 times before I would go do a bunch of EROs. But that's just me. I just like the theory problems. So in the engineering classes, do they like usually prove stuff, or they just kind of say, here's the formulas and just to do the problem?
Solve it pretty much.
There's a problem, solve it.
Really?
Yeah.
But they don't have like oh, here's the background behind it or whatever?
Rarely.
Oh, gosh.
We're not,
I knew there's a reason I didn't become an engineer.
we're not,
They mention it, but they don't work on it.
They don't work on it. Okay.
we're not math majors.
Okay. So I wouldn't survive over there. In other words, is what you guys are saying. I love the theory too much. I'd have to like stop and explain every little thing. Cause that's just the way I am. I've never been good at just accepting something, like mathematically, I mean. Like somebody hands me some formula, I'm like, well, where'd the formula come from? I wanna understand it better. I don't do well with just kind of trusting something, but that's just me. Okay, anyway, let's do this theoretical problem. This is actually a true or false question. Not a huge fan of true false questions on exams because sometimes they feel tricky to me, but that's okay. We'll just ask one here. This is a review session. A is 7 by 9. With nullity of A equal to 2. Then here's the true false. The true false would be, is the row space of A equal to R7? I'd like to review the background behind nullity and row space. We have a 7 by 9 matrix. It might even help to kind of, sometimes I will even do this. I think I'll do it. I'm going to draw 63 dots on this board. 7 rows, 9 columns. Whoever's next door probably is wondering if I'm tapping. There's an emergency. Come on over here and help us. 7, 9. 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 7 by 9. Thank you for humoring me on that. That's kind of the shape of the matrix. And so the question is, will the row space of A be equal to R7? Any thoughts here? Yeah, maybe not quite ready for the answer yet, but like what would be relevant would be something like the rank nullity theorem. So I just want to remind us that this is a really important equation, as you know. If we add the rank of a matrix, so I'll just start with that. And again, maybe you don't know the answer totally, but you know that this is important and it's probably related. Just write it down. It cannot hurt you to write it down, even if it turns out it's not right or it's not relevant. My eyes are just gonna go over it. I'm just gonna go to the next thing. So it's not gonna hurt you to write this down. Now, in this case, what is n?
7.
N is 9.
And
M is 7, N is 9, right? We always do M and N like that. Okay. So what could we figure out from that?
so
Okay, yeah, because the nullity was given as 2, so I can solve that for the rank of A. The rank of A would be 7. And so that's helpful. And I actually, if we remember something, I don't know if I have this ready to turn on. There was a handout that we looked at when we were getting ready for, I think it was the second midterm. Okay, this is the integration table. Let me go to the. I feel like I'm the only one who uses this classroom. This thing that I just had up last night is still here. I guess nobody did anything with it. But no, I was gonna show you this recap of 4.6, 4.8, 4.9. I don't know if you guys remember this thing. This was under your pillow every night for 2 weeks before the second midterm. Yeah, the chart at the bottom is super helpful about all of this stuff. And I do see the rank, which we just figured out at 7. The rank is the dimension. It's in the dimension of either the row space or the column space. They're both 7-dimensional for this example. Okay, so in other words, the dimension. So the dimension of the row space of A is 7. Because the rank is what the dimension of the row space is. So I'm connecting the question now, because the question says, is the row space of A equal to R7? So we now have the dimension of the row space equals 7. So it's a true false item. Again, I probably wouldn't ask it as a true false, but any thoughts yet about whether this is true or whether it's false? It seems true, doesn't it? Trying to bait you guys into it, right? It seems true because I said the dimension of the row space is 7, and oh, well, row space equals R7, that fits perfectly, right? Because the dimension of R7 would be 7, and that matches up with what we seem to be saying here, right? But what you need to remember, my friends, is that there are lots of things that are 7-dimensional besides just R7. P6 of R is 7-dimensional. I could make, all matrices of this form. All matrices of this form are 7-dimensional. I can bust out 7 letters there, right? So there's tons of things in this universe that are 7-dimensional. So just because the row space of A has the dimension of 7 doesn't mean that it equals R7. And I was trying to kind of get you to think that way. It's actually false. I was getting you to think that way by drawing out this little picture here. If you look at the rows of the matrix, remember guys, the row space of a matrix is the span of its rows. If you look at any one of these rows, you can see how many dots are in that row. 1, 2, 3, 4, 5, 6, 7, 8, 9 dots in that row. Well, if there's 9 slots in these row vectors, then we're not talking about R7, right? R7 is exactly the vector space of vectors with 7 slots. So here I'm drawing rows that have 9 slots. That's not going to be R7. So what we can say that would be correct is what we can say is that the row space of A is a 7-dimensional, we know that it's 7-dimensional. It is a 7-dimensional subspace of R9. So again, for those of you who are on the video, I'm going to move you over here for just a second. So we're using this recap summary handout. If you look at the row space of A, it is a subspace of Rn. In this case, n was 9. So we have a 7-dimensional subspace of R9, but that does not make it equal to R7 at all. Right? You gotta be a little careful about that. So this is actually false. As a quick follow-up, as long as I'm thinking about it, what about the column space of A? So let's just tack this on as a quick little follow-up question. is the column space of my 7x9 matrix with nullity of 2, is that equal to R7? Well, now we're talking about the span of the columns. If I look at one of these columns, I can see that there's 1, 2, 3, 4, 5, 6, 7 dots in that column. So the columns do at least have the right number of slots. In fact, it says it here, doesn't it? The column space is a subspace of Rm. So the M is 7 here. So that is encouraging. And not only that, the dimension of the column space is the same as the dimension of the row space, which was 7. So actually, in this case, guys, the column space of A is still 7-dimensional. It is 7-dimensional and it is a subspace of, in this case now, R7. The span of the columns is going to be within Rm, and M is 7. Well, guys, if you have a 7-dimensional subspace of R7, then you are talking about R7. There is nothing else it can be. Right? You have something that's just as big as R7, that's inside of R7. Well, that's R7, right? That is R7. So this is a yes. That's kind of interesting. The row space does not equal R7, but the column space does equal R7 in this case. Yeah, go ahead.
So for the row space, if if A is a n by n matrix, that would be true.
If A was an n by n matrix, I need to know, is this a, so these are both 7s?
Yeah. Square matrix.
I don't think that it doesn't matter if it's square or not. If that's a 7, then I gotta change this to a 7, and then this would change to a 5. And so as all the numbers are being thrown off, so I don't think we can make quite such a quick assumption there, but yeah, that's a good question though. Okay, are we doing okay? Everybody good so far? There is another topic I wanted to go over. We don't have a lot of time here. I'm gonna go maybe 15 more minutes or so. But I did it last night, but I want to hit it again because it's a big topic that we haven't looked at recently. By the way, I don't know if you've noticed this. I've not been doing so much review on chapter 9 or chapter 8. The stuff that you just took this exam on recently, and many of you did the redo exam as well. Make absolutely sure. There are some people who do not know how to do the W diagram thing yet. I know that for a fact. And there's some people who do not know how to do the Floyd process yet. If that would happen to be you and you have questions about it, I'm not going to go over that here, but I would love to just review it in my office hours. Either tonight or tomorrow or whenever. We don't have a lot of time, but it is definitely something that we need to get down. I feel bad because the way the class is structured, we learn that stuff right at the end, and it's not like a huge amount of time to really get it down. So I do understand it's challenging. Most people have got it pretty good shape, I would say. But if you don't feel so good about the Floyd method, the trouble with it is those problems are always worth a lot of points because there's so many steps to them. So if you're not getting those, wow, you just get hammered. Some people, that's what happened on the third midterm. They got the Floyd problem wrong, and then they got the defective system problem wrong, and that together, that was 25 points or something. So it really can hurt you quickly. So definitely make sure that you review that and ask me for help if you need it. I'm always happy to help. For sure. But I do want to ask, I want to turn to a different topic right now that has not been discussed at all for quite a while, which is inner products. I did it last night in the review a little bit, but I haven't done anything on it tonight. So I'm going to make an example. This will be different than the one I did last night. But I'm going to consider the vector space of continuous functions from 0 to 3. So these are just calculus functions defined on the interval from 0 to 3, and then I'm going to define a formula. Remember that if I'm talking about inner products, this is a attempt to put a geometric component to a vector space. And so you have to be given an inner product. So I might define how to take the inner product of two calculus functions. And I'm going to make up a formula. It would be a really good chance that I would probably try to, I mean, I could give you something you've seen before, but I also might give you something weird that you haven't seen before, like I'm gonna do this one here. I'm gonna take t times f of t times g of t dt. Now, the sort of most natural inner product dealing with functions would have been this one. Actually, this one you're gonna see in those engineering classes. Most likely they're gonna throw this particular, it might not be interval from 0 to 3. It could be any a to b here, doesn't matter. This one is the second most famous inner product ever to be created behind the standard dot product. So number one inner product that everybody knows is the dot product. Number 2 on the list is probably this one. And you're taking two vectors from this vector space and you're calculating this number. Remember, the inner product of two vectors is always a number. And I am throwing a little bit of a wrench in this by putting a t there. And I'm asking you, what I'm gonna ask you now is this a valid inner product? To answer this kind of a question, you will need to know the axioms of an inner product. And I'm going to quickly write them down. I wrote them down yesterday as well, but I'm gonna do it tonight as well, because I know I don't have all the same crowd. The 4 axioms, right? The first one is that when you take the inner product of a vector with itself, you should always get a number that is at least 0. And it would only equal 0 if the vector that you actually started with was the 0 vector. So that's the first one. It kind of has 2 parts, to be honest with you. You almost think of this as 2 axioms, but they kind of go together. And then the second axiom, again, some of you may not need to write this down. It's obviously probably in your notes, but I'm just, especially if you were here last night, you've definitely seen me write these down. If I switch the order of the 2 vectors, nothing changes. The third one is pulling out constants. So in the particular, from the first entry of the inner product, if I take c times v, inner product with w, well, I should be able, hopefully, if I have an inner product, I have to be able to pull the constant right out. Remember, c is just a real number and the inner product of 2 vectors is just a number. And last but not least, whoops, this should not be an equal sign, this is a dot. Bullet points here. The last one is the one about addition. If I have v1 plus v2, inner product with w, okay, I can split that into 2 parts as well. So inner product of v1 with w plus the inner product of v2 with w. Okay, so you do need to know these. So I've written them down here for you one more time. I know you all learned them a couple months ago, but we're just gonna reiterate this one more time. So the question is, will this inner product satisfy those 4 axioms? That's actually what the question is asking here. So we have to go through them kind of one by one. If any of these axioms fails as we go along, we could stop and say, no, it's not a valid inner product. Making sense? Okay, so let's just try. I'm not gonna go through all 4 of them. Let's try. In fact, I might not make you guys do that either. I might say pick 2 of them or something and then just do whatever you want. Let's just pick the first one. I always like to do the first one because this is the one that sometimes gets us hung up. And in last night's review, it actually did on the example I did there. But let's see if this works on this example here. So I'm just gonna take the inner product of f with f. So this is just where you put the same vector in both slots in this formula. And we're just gonna ask ourselves, is the answer at least 0? Okay, so how's that gonna look? It's gonna be an integral from 0 to 3 of t times f of t twice, which would be f of t squared times dt. And my question for you guys is, will this be greater than or equal to 0 at the end of the day when I do that integral? If I square something, for sure that's positive, right? And I'm multiplying it by t, where does t exist? Between 0 and 3, which is actually also positive. So when you're thinking about the kind of values you'll have inside this integral, you have a positive number times something that's for sure positive. I don't even know what f is, but it doesn't matter. This will be positive because it's squared. So you have positive times positive, guys, which is positive. When you integrate, so you are integrating a function from 0 to 3 that is above the x-axis, right? So this, we all learned back in our calculus days, we learned that the integral represents the area under a graph between a and b. And if that function is above the x-axis, that's positive area. So I would be very confident to say that that is greater than or equal to 0. Definitely. And the only way that it would actually be equal to 0 is if the f itself was just constantly 0. Then you really are integrating literally 0 in here, and that would be 0. But anything else, if your function was not just all 0 everywhere throughout that domain, then you actually have a curve that's gonna ride above the x-axis a little bit and create some area for you. So I would also say this is equal to 0 only if f is equal to 0. I'll put a check on that. Absolutely believe that. This is like the first axiom. Yeah.
Is it only if f equals 0 or t equals 0?
F is the actual vector here. So that's actually, the f is playing the role of the v in this example. The t is just a dummy variable of integration. It's kind of just a device for doing the integral. It's not really the essence of the vectors that are in this space. Good question. Usually if I give people a choice, people will usually like to pick the second one. This one's an easy one, right? The inner product of f with g. Okay, so I do the integral from 0 to 3 of t, f of t, g of t dt. And the question is, can you switch it and put the g first and put the f second? And you all know that, right? You could just, inside this integral, there's nothing stopping you from doing g of t times f of t. So you just switch the order of those, and then, there you go. You have the inner product of g with f. Do you guys notice how neatly formatted this is? Right? I have my white space over here, and I don't fumble around on both sides of the equal sign. I try to be very organized. One step goes to the next, goes to the next. I'm only operating on the right side. I talked about that also when you are verifying linear transformations, that they respect addition and they respect scalar multiplication. I always like it formatted like this, so that it's just easy to follow the logic of it. So this axiom is also true. And it turns out that this is a yes. You guys can probably see that if you had a constant inside your integral, one thing you know about integrals is constants can be pulled out of them. And so if you just do that, you'll verify the third property easily enough. And the fourth thing that you know about integrals is that when you have a bunch of things added together inside the integral, it gets split up a plus sign. So integrals do respect addition. I even think we had a homework problem about that. That if you make a linear transformation that is based around performing an integral, that will be linear. It will respect addition and it will respect scalar multiplication. So these last two axioms here are actually not very hard to show. But I think I will skip that because I've only got a few minutes that unfortunately I can't run like super late. I was telling people last night, I used to do these review sessions that would go for 6 hours. And nobody would ever leave and I would just keep doing problems. And I finally have to say, you guys want me to stop? But that was back when I was like 20. And also it wasn't when I had to have an office hour the same night. But I did want to do one thing with this before we go. Where is it? Oh, I wonder if I lost that page. I lost that page. It's okay. I'm gonna make it up. We're gonna make up a follow-up question here. I would like to do the following follow-up question with that same inner product follow-up. Find the angle between f of x equals, let's go with x squared plus 1 and g of x equals x to the 4th. So we're doing geometry now in what was a vector space. These are just calculus functions. They live in V. And I just want to find the angle. So I guess the one question here is, does anybody remember how to find the angle between two vectors? It's a cosine inverse, actually. So the theta, the angle is the arc cosine or the inverse cosine of, I'll just remind you here, you take the inner product of the vectors. So in this case, we have f and g. And then you divide by the norm of f as well as the norm of g. So this is an equation, actually comes more or less from Calc 3. That's where they kind of came up with that as a definition. So this is the angle between two vectors, and each one of these parts can be calculated using the formula in the box over there. Right, so if I want to know, maybe before we continue, let's just calculate some of the things we need here. I need to know the angle between f and g. Make sure that I'm getting all this. The angle between f and g, the inner product between f and g. So we have the integral from 0 to 3 of t times f of t. Notice I have to change the x's to t's here to just use my dummy variable of integration. And then I have a t to the 4th as well. So this is just t times f of t times g of t. It's exactly what's in the box over there in that formula. So let's simplify this before we actually do the integral. This is actually, if I think I did this right, this is t to the 7th plus t to the 5th. Oh my goodness, what have I done? Does anybody know 3 to the 8th? You have a calculator there? Is that a calculator on your phone? Or is, I might need somebody with a calculator because I'm gonna do 1/8 of t to the 8th plus 1/6 of t to the 6th from 0 to 3.
65, 61.
For 3 to the 8th?
Yeah.
6, 5, 6, 1 all over 8 plus, and what's 3 to the 6? Wait, don't tell me. 729. Thank you. 729 over 6. I had a grade school math teacher. She was really harsh. She would make us come in and give us a piece of paper, and she'd give us 5 seconds to write down, and we had to memorize like the perfect squares up to like 50 squared, and then we had to do like the cubes up to, I forget, 20 or whatever. And then she'd give us 5 of them, and she was eagle-eye watching us, and she would give us like 5 seconds to just write them down, and pencils down. And she'd collect our papers, and we got graded on it. It's like, oh my gosh. So I had to learn some of these things, but I didn't get up to the 8th power of anything. Anyway, so this probably simplifies, but I guess for now, I'm not gonna worry about it. So you'd have to make a common denominator and simplify that. I'm not gonna bother. So we'll just leave it like that. Let's do the norm of f. Oh, does anybody remember the formula for the norm of a vector? Square root of the inner product of f with f, exactly. So we just take the square root of that. Remember that our first axiom over here this first axiom tells us that what's under that square root will not be negative. So I am taking the square root of a positive number here. This will be the square root of the integral from 0 to 3 of t times, and then I have to do t squared plus 1 times t squared plus 1.
If it's okay to change t to x.
Yeah, yeah, if you don't like the t, you can use an x everywhere. Yeah, it's actually totally optional. The one thing you don't wanna do is mix them. Because mixing x's and t's would be maybe confusing, but if you prefer x's, you can certainly do that. And then I think I'm just gonna leave that. I'm on low energy at 9 p.m. You all could do this, plug in the numbers, take a square root, whatever. So the norm of g, this one would be the square root of the integral from 0 to 3 of t times t to the 4th times t to the 4th dt. And so that one, I guess I'll take this a step further, because at t to the 9th I can do, it's 1/10 of t to the 10th from 0 to 3. So anybody can calculate that as well, assuming you had a reasonable calculator. I didn't want to use the limits from 0 to 1 because I use those all the time. I just wanted to make it clear, guys, you can choose any limits here you want, make a different problem. If we find out, quick question, if we find out that this angle is not 90 degrees, which by the way, I don't think it's going to be because the numerator here is not 0. If we find out that that is not a 90-degree angle, then that would mean that these vectors are not orthogonal. What if I asked you to give me an orthogonal basis for what they span? One last thing, I'm not gonna calculate any of those integrals because it's kind of boring. But this would be, half the battle sometimes is just, what is the question asking me to do? Right, so if I had another follow-up, it might look like this. Find an orthogonal basis for the span of x squared plus 1 and x to the 4th. This would be another question we could ask here. What are you gonna do? Awesome. You see, any question like this, find an orthogonal basis or find an orthonormal basis, you want to be thinking about using the Gram-Schmidt process to do it. So these vectors would get labeled as V1 and V2. And then I would give you the Gram-Schmidt formulas. Remember that you turn these into W1 and W2. These are not the same W's that we just learned about last week, right? This is the earlier topic. W1 is just V1. And then I'm gonna give you these Gram-Schmidt formulas, so you don't have to worry too much about this, but just for now, I can write it down easily enough. W2 is simply V2 minus this inner product of V2 with W1 divided by the norm of W1 squared times W1, most of which I think we probably, if we actually worked this out, we would have had a number already for everything here. So this inner product is really just the inner product of x to the 4th with x squared plus 1. It would literally be this. So this is what goes on top here. And then what goes on the bottom would be the square of the norm of f. Notice if you square a norm, all you're effectively doing is getting rid of the square root. Yeah. So then you just have to take the inner product, you just have to take the part that's under the radical. Was there a hand on something? Yeah.
Yeah, I had a question about when you present something as a basis, when you present it as a span, the two vectors are already aligned, right? Because you present it as a span. It's a spanning set.
They wouldn't have to be. You gotta stop giving me good ideas. Technically they wouldn't have to be. I could say first thing you have to do is reduce it to a basis. You guys have seen these problems before, right? I think even on the redo midterm where you have a list of vectors, but they are LD. And you test that by laying them. We did this last night. You'd lay them into the columns of a matrix. Any unpivoted columns Any unpivoted columns correspond to the vectors that you must throw away to remove the linear dependencies. Right, and then you just keep the pivoted columns only, the vectors that are pivoted, and that then is a basis. In this case, it's easy because these are clearly Li. Can I say that word clearly? They're not scalar multiples of each other, and there's only two of them. So they are definitely not, these are definitely Li, so this is a basis, but you are right, I could have. What's to stop me from saying, 3x to the fourth here? That would be pretty obvious. You look at that and say, well, I can see that this third vector is it's not even a basis yet, I gotta get rid of it. So you get rid of it. Once you have it down to a basis, then you would orthogonalize it, if that's what they wanted, and that's where you use the Gram-Schmidt process. And like always, guys, if you can tell that you need to use the Gram-Schmidt process or you just don't have the time for it, at least write these words down on your paper so I can give you 20% of the credit or something for it to say that the person knows at least what they're supposed to do. Because that's worth something. That's part of what this class is about.
Just remind us the difference between orthogonal and orthonormal.
Yeah, great question. So does anybody else want to take that question? What's the difference between orthogonalizing the vectors versus orthonormalizing them? Sorry? Not sure? That's okay.
Is it orthonormal makes it like a unit vector?
Yeah, the orthonormal basis is where the vectors have been normalized to have a length of 1. So what you have to do for that is, if I wanted to do that, and I'm glad that you asked this question because you do have to read these questions. I could have said find an orthonormal basis. Then what you have to do, guys, is go to U1 and U2. And the way those vectors would look, just to remind you really quick, you simply take the W's that you just figured out and you normalize them by dividing by their norms. This is an extra step, and it's usually kind of a pain because you've got square roots usually that end up in the denominators here. It's just literally a stretching though. You're just simply stretching the vectors or shrinking the vectors so that they have a length of 1. Yeah, so but that is another thing that I could ask you about. There were a couple of theoretical problems about orthogonal and orthonormal bases. I specifically remember one in the group work. I think group work 9 has a nice if you're interested in reviewing inner products efficiently without redoing all the homework, there's like 2 problems on group work 9 that are both probably really worth looking at again. So anyway, I kind of need to call it for now because I know I've got some students who are planning to attend my office hours at 9 and I'm a little bit late, but we've done pretty good here, but I'm sure I didn't cover everything. If you didn't come to my review last night, I wouldn't hesitate to recommend that you try to watch last night's review if you have time. And again, you can come on Tuesday or on Thursday. It's whatever is better for you. And I wish you all the best with all the studying. And let me know if I can be of any further help. You're welcome. Just gonna get this turned off. Hit the board. Can you? Yeah. Oh.